This is a video for section 3.5. It is about logistic models. Logistic models have the functions that look like the following, where C, you'll notice on top of both, is the limit to growth. A logistic function is similar to an exponential function in that it grows and grows and grows, but it has a top. It has a point to where it can't grow anymore. So you almost have an asymptote. At the top has an upper bound, and C is that limit to growth, so it's as high as it could grow. And we look here at the graph, you see the line here where the K is that dashed line that represents the limit to growth, and that's how high that it's going to go. So you can see how in the beginning we have some growth, very fast growth like an exponential, but then it flattens out instead of continuing to go up and up and up. Now, first thing we need to understand is how to find the logistic function that satisfies the given conditions. A lot of this lesson today is going to have to do with solving equations and manipulating variables, learning how to work problems forwards and backwards. So we have our initial value, which is 10. Right? That's kind of like our A. We have our limit to growth, which is 40. That would be our C. So you want to make a note. This is A. This is C. And it's passing through this point 120. So 1 is still our X. And 20 is our f of X. So we have our function, f of X equals C over 1 plus A times B to the X. When we go and do this, we need to start plugging some things in. We said A is 10, C is 40, and we have our X and our f of X. So we're going to end up with 20 equals 40 over 1 plus 10 times B to the first. Now we gotta find B. We don't know our rate. So that is, in order to write our function, we have to find our rate. We're not given that value. So this is where we talked about. So B to the first is just B. So what we gotta do is we gotta get the B out of the denominator. So we need to multiply both sides by this whole thing. It's gonna cancel out those on that side, and I'm gonna end up 20 times 1 plus 10 B equals 40. Well, I want to get rid of my 20, so I'm going to divide both sides by 20. That's going to cancel these out. It's going to leave me with 1 plus 10B equals 2. Take away my 1. 10B is 1, so B is 1/10. So then I go to write my function, and it's f of X equals 40 over 1 plus 10 times 1/10 to the X. And that's my final answer. So you see, there's a lot of algebra and just manipulating variables and moving things around happening right now to solve for B. But we use all of our normal algebra rules to do this. So move on to the next example. Remember, our initial value is A. Limit to growth is C. And we have X and f of X. So we go to our function. F of X equals C over 1 plus A times B to the X. And I plug in my values. So I get 24 equals 60 over 1 plus 12 B to the first. Okay, remember, manipulating our variables, gotta get this out of the denominator. So I multiply both sides, I end up with 24 times 1 plus 12B equals 60. Divide both sides by 24. I get 1 plus 12b equals 5 over 2. Then I gotta take away my 1. I'm end up with 12b equals 3/2. Gotta divide both sides by 12. And b equals 1/8. So my function becomes f of x equals 60 over 1 plus 12 times 1/8 to the x. Alright. Now in both these cases our x was 1. But x is not always 1 and always given that point. So let's check out the next one. Here, work through this. Remember I got my a and my c, x, f of x. So I'm going to have a little more work to do when I go to solve this guy. So 15 equals 30 over 1 plus 5 times b to the third. Well, this time I'm going to have some work to do at the end. First couple of steps are still the same. Multiply both sides, so I end up with 15 times 1 plus 5b cubed equals 30. Divide by 15. 1 plus 5b cubed is 2. Take away 1. I end up with b cubed equals 1/5. Well, now I have to pay attention because it's not just b equals 1/5. I get b to the third equals 1/5. How do I undo something that's cubed? I gotta take the cube root. So the cube root of 1/5 is my b. So b equals, ends up as 0.584. So when I go to write my function, f of x equals 30 over 1 plus 5 times 0.584 to the x. Do I have to have a whole number answer for b? No, b is my rate. It can be all sorts of different things. So I'm going to have you pause the video now at this point and attempt this problem on your own. Notice here, our x is a 5. So when you get to that point, keep in mind, I need to do the 5th root to undo b to the 5th. So pause the video, attempt the problem, then come back and check your answer. Go ahead and check your answer. Over here is my final function. You should have gotten b equals 0.715. So that's the first kind of thing that we're going to do, is writing the logistic function given some of the information. Second thing we use these for is story problems. First example. Based on recent census data, a logistic model for the population of Dallas T years after 1900 is as follows. According to this model, when was the population 1 million people? So if we're looking for when, it means we're looking for a time. So we need our t. So we're going to set 1 million equals we need to solve for t. So a lot of things happen similarly to what they did in our last. We're going to multiply both sides by the denominator, and then we're going to divide by our million. So we actually end up with 1 plus 21.602e to the negative 0.05054t equals this fraction. And I got that fraction by taking 1,301,642 divided by a million. Now I go back about my business, subtract 1 from both sides, and I'm going to get 21.602 0.602 e to the negative 0.0504t equals this. Then we divide by 21.602 and we get e negative 0.05054t equals this value. Now we take the natural log of both sides in order to undo the e. So I get negative 0.05054t equals the natural log of 0.013. I'm going to divide by the negative 0.05054. Now, you need to make sure when you're doing this that you don't round too soon. I rounded here after I divided this by the 21.602. That's my first rounding, but now I want to type in this whole thing as I see it. And I get 85.928. Now remember, when you're typing this in your calculator is going to insert a parenthesis right here. So you need to close that parenthesis before you do your divide sign. Okay. Now this is 85.928 years. The question asks, when was the population 1 million people? So that means in what year? So it started at 1900. So the answer would be in 1985. Or between 1985 and 1986. Because we're close to 86 on our answer. Okay, lots of moving things around and manipulating variables today. Let's go on to the next question. Watauga High School has 1,200 students. Joan, Louise, Ted, and Emily start a rumor, which spreads logistically so that this models the number of students who have heard the rumor by the end of t days, when t equals 0 is the day the rumor begins to spread. How many students have heard the rumor by the end of day 0? So, by the end of day 0 gives me a time, so I'm going to plug 0 in for t. So S of 0 equals 1,200 over 1 plus 39 times e to the negative 0.9t times 0. You're going to plug this whole thing into your calculator. Make sure you put parentheses around the 1,200 before you hit your divide sign. And you put parentheses around this entire thing, so your calculator knows what to do. Then you're going to get S of 0 equals 30. So 30 students heard the rumor by the end of the first day, or by the end of day 0. Okay? So that was a simple plugging in for time, but you have to pay attention to what the question is asking you. Here, same question, same model. How long did it take for 1,000 students to hear the rumor? Now instead of plugging in for t, I'm plugging in for S of t. I'm back to having to solve that long problem. So 1,000 equals 1,200 over 1 plus 39e to the negative 0.9t. Right, multiplying both sides, so we get 1,000. I'm going to divide by 1,000. Take away 1. So I get 39. E to the negative 0.9t equals 1/5. Divide by 39. And let your calendar or your calculator do the division for you. Take the natural log of both sides, so that the e goes away. And divide by negative 0.9. and you get t equals so at the end of 5.85 days, 1,000 students have heard the rumor. As you can see, there's a lot of solving equation skills going on here. It just looks a little different, but all of our skills are still the same. Now, the next couple of slides are based on the same example. I'm going to ask you to pause the video after each question and attempt it yourself, then come back and check your answer. The example for this is the same example. Using 20th century census data, the population of New York State can be modeled by P of T, where P is the population in millions and T is the number of years since 1800. Based on the model, what was the population of New York in 1850? Go ahead and pause the video, then come back and check your answer. Here's the answer you should have gotten for this example. Go ahead and check your work. Same question now. What will the New York State's population be in 2010? So remember, this is all based on 1800. So by 2010, that's been 210 years. So I'm going to plug 210 in for t. So if we plug 210 into our function, we see that we have 19.161 million people at the end of 2010. Next question, what is the maximum sustainable population? Remember, our limit to growth is this number up here in our function. So the maximum sustainable population is 19.875 million people. Make sure you label things correctly. Go ahead and go through and complete the worksheet for your homework.